see you like 100% sure next Monday, okay? All my other labs are actually doing their labs in my presence on WebEx, except you, because your section is beyond 5 p.m. and there's no one to be able to open the door for you and to help me out settle WebEx in the lab, you know? But see, since you are one section only, yes, you are one section. Am I wrong? No, I'm not wrong. We are a bit flexible throughout our schedule, which means I can play around with those labs. And next time I see you, we can follow a different scheme. Okay? Please, at any moment you feel to talk about anything related to schedule or midterm or anything that keeps you a bit anxious, let me know. All right? Because I need to be transparent through schedule. And I need you to know everything. Now, concerning the previous lab reports, I corrected, I think, 2 groups, which means around 6 students. I was so impressed by the graphs you were doing on Excel, so impressed by the slope, units, by the way you do averages and RMS. And this took me with a great expectation. So now I'm not worried anymore, but I'm a little bit suspicious. Are you guys doing those lab reports with the help of someone? And it's okay if you are, as long as you know what you're writing. Because there's no way Physics 111 students can present like those pretty lab reports. Selena, you're so smart, like you're incredibly smart. But my medical students, my medical school students are not delivering such pretty lab reports. Mama, even with you, Giorgio, even that, the font, the format, the presentation. I have no doubts, Andrew, that you are that good. As long as you understand what you're doing, that's okay, that's manageable. I don't want you to be surprised later on in a midterm not knowing to do the RMS error. Why am I saying that? Because now in the coming lab, you have to do RMS error and you have to do so many things. And I just want to know that if you are up to the level or not, okay? Anyway, so far, beautiful labs number 2. I'm not done. You're going to receive your grade very soon. Concerning lab 3 was projectile motion. Please, if you were not with us last week, I already, okay, that's my charger. That is, wow, I mean, this is a charger. So concerning lab 3, I already recorded this session for the students who were not with us. Please make sure you watch it again. Okay, so watch lab 3 again. I'm gonna give you the results right now. Let me show you what results to expect. By the way, let me go back to the lab reports for you to know what I'm talking about. So this is lab 3, projectile motion. We discussed most of it in the PowerPoint presentation, and you have the recorded value, the recorded session. Also, so if you watch it again, probably you can answer question 1 easily, you can answer question 2 easily, and so on, okay? You only need the measurements. So I thought if I give you those values that you can see in red, you should be able to do the lab report. On one condition, next time I see you, I'm gonna give you this empty or something similar, and you do the experiment to fill it in. And it's gonna be on paper, which means you don't need to do the lab report anymore. This is the first time we do this, do the lab report first, then the experiment. But I thought probably this is gonna be, hello Magali, this is gonna be awesome just for you to speed up the work once I'm back to the lab, okay? So you have for next week to present lab 3, and those will be the values given to you, okay? So Michelle is saying we're not having any help, we're just taking your notes and help very, all right. So basically I'm willing to help fully. That's why I don't see why not. You should do well. Nasim, hello. I'm glad to see you here. You are a bit late though. Okay. So now that's it concerning lab 3. I expect you to check the presentation again, and I believe everything is on Blackboard, isn't it? If I go back to Blackboard and I check lab 3, you should see, yes, the recorded meeting, the presentation, and the experiment. What was the experiment? The experiment was an old YouTube video of how things should be. You don't need the experiment. What you need is the manual and the lab report for you to be able to fill them in, and you need a slot to present your work. Try to do that in the couple of days. Don't give yourself more than 3-4 days, okay? That's for lab 3. Now for lab 4, I'm gonna go over it, and I'm not expecting you to present any lab report yet until I see you next week. Is that understood? Probably I'm gonna summarize all this in an announcement, especially for the students who are confused or the students who are not with us, okay? All right, now what is the next lab 4? It's motion on an incline, okay? Let me move the participant names away a bit, just a bit, and the chat just a bit so we can see all the slides. So motion on an incline is a very important experiment. What I like about it is it could be a reproduction of free fall. You know, free fall experiment where the acceleration equals gravity. This is very similar to it. However, the acceleration is not gravity, but a function of gravity, okay? I'm gonna be quick, especially for the students who need to leave us at 6. I will start discussing the force diagram, and I really need your input, okay? In general, during an inclined motion, Newton's second law, because every motion would start from Newton's second law. I need to discuss the experimental setup, because next time I see you, we're not going over this again. Like now I'm telling you what's in the setup experimentally, and next time I see you, start the experiment right away, because you're gonna be doing lab 3 and 4 together. Motion graphs are a bit tricky and confusing. However, so far I can see that you are understanding motion graphs. I mean xt, vt, and at graphs, and probably you're gonna find this okay. And eventually how to measure the acceleration experimentally and the lab report right away. If I give you this presentation and a recorded session that you can watch on Sunday evening, you can come Monday to the lab ready to start your experiment directly. Do you think it's a good idea?
Can you repeat that, please?
Yeah, if I give you this presentation and if I give you a recorded session and if I ask you to watch it Sunday evening, do you think on Monday you can come and start the experiment right away? All right, so this is
I think so, yes.
Yeah, this is my expectation from you. I would love to hear more feedback from Giorgio, from Nassim, and from Magali, okay? All right, this is an inclined plane. It could be any box on a plane that is with a certain angle with the horizontal. And this is a diagram we can draw onto, okay? I'm gonna move this a bit. And I'm gonna pick a pen, and I want Magali to help me. Hopefully she's there, she can hear me. Magali, I want you to tell me what are the forces on the box. Very simple. And I'm assuming that the box is sliding on the incline without any friction. Yes, Magali.
The weight.
Yes, the weight. I'm gonna call the weight mg. I don't like W, and I don't like force of gravity. mg, if you don't mind. Anything else?
ما في frottement. I don't know how to say.
All right, friction. Yes, it's okay if we say it in French. If you want, we can say we have friction. However, this is without friction. Let's assume we have friction that is in this direction, and we can delete it later. So this is friction. Yes, Magali, anything else?
No.
All right. Giorgio, would you like to add any force?
The normal.
The normal force. Who's talking to me? Magali again? Michelle? Okay. So Michelle, yes, Michelle is saying we need to add the normal reaction. I cannot see this. Let me see if dark blue is better. So this is the normal reaction. We can call it N if you want. All right. So we have good news for Magali. I'm gonna delete the friction because they say without friction. However, that's a source of error because we all know that we have friction. You will be given a track that is very smooth and a cart that is super fast, and friction is really, really, really small. We can neglect it, but it's always there, okay? So you can list it under sources of errors. By the way, the sources of errors you wrote, you sound like a professional. And to be honest, I still believe that you have references because none of the students know how to write these lists of these sources of errors like
You mentioned them in the beginning of the session, and I took notes of them on my
Yeah,
copy
I'm
book.
so
You can
proud
check
of
them if
you.
you want.
I'm so proud of you. No, I'm not saying I don't trust you or anything, but I'm just saying how impressed I am. I'm really impressed. I'm really impressed. I'm gonna show you other students' lab reports and you're gonna be really surprised. Newton's second law, sigma F equals ma. I'm gonna go back to our diagram, which looked like this. With the help of Magali, we drew the forces on the box, and that was the box, right? We drew mg, and we drew the normal reaction, okay? Every time you are given an inclined plane, you need to consider, let me try with orange. We need to consider the x-axis to be along the motion. Always take the x-axis along the motion. This is key. So if the motion is downward, I'm gonna take the x-axis to be downward, and I'm gonna take it along the incline. Automatically, the y-axis is gonna be perpendicular to it, okay? And now, instead of dealing with mg, I'm gonna grab mg and I'm gonna delete it. Instead of mg, I'm gonna deal with mg sin theta and mg cosine theta. And you're gonna hate me for this. Probably not, I don't know. Mg cos theta. By the way, this is theta, and let me draw the incline again in here to explain quickly how come mg is now, so this is mg, right? This is mg, this is theta, and the drawing, the x-axis is this, and the y-axis is this, right? If you really think about it, this is theta as well, because mg is perpendicular to the horizontal plane. And the y-axis, which is here, is perpendicular to the inclined plane. So you end up with theta and theta to be similar, okay? But since the angle given is between the force and the y-axis, you take mg cos to be for the y component and mg sin to be for the x component. It's opposite to what you got used to. You got used to say the x component is mg cos and the y component is mg sin. But since theta is with the y-axis, that's why I switched them. Do I make sense? Please ask in the chat if you believe it's a bit tough and you want me to explain it again.
No, it's clear.
Is it clear? All right. So we have the weight. I need to forget about the weight, and I need to think, instead of mg, I have mg sin and mg cos. Now, if I go back to sigma F equals ma, what you see in bold is a vector parameter. So instead of writing this equation, I can either write the x component of it or the y component of it. If I take the x component of it, it will be written as the net force equals ma. Along x, the only force is mg sin. So mg sin theta is equal to ma, right? This is along the x-axis. I can easily cross out the m's, and I will end up with a is equal to g sine theta. Okay, so what was again the acceleration for free fall? Who remembers? Andrew remembers. I remember Andrew was so happy during free fall. Andrew, what was the acceleration during free fall? Come on, it's easy.
I can't hear you. What?
Yes, acceleration for free fall.
Equals minus g.
Exactly. What is now acceleration for the inclined plane? Inclined motion. Instead of saying minus g, we say minus g sine theta. All right? Minus d means downward. So you don't need to say minus as long as you say down with it. Since my x-axis is downward, that's why I did not say minus, but definitely my acceleration is downward. Okay? So now the experimental setup. You will be given a track in aluminum. You're gonna touch it. It's gonna be cool, like cold metal, and it is a bit heavy, but not too heavy, like any other metal will be heavier. and you're gonna put a cart on it with very fast wheels, and you'll be happy to play around a bit with the cart. I think the cart is around 500 grams, but every cart has its mass written on it and measured with a digital measuring tool. Ms. Jinan did the measurements for us. You will attach a bumper at the end of the track because you don't want your cart to go down to the floor. It's gonna fall down, it's very fast. You're gonna pick very small angles, 9 degrees, 7 degrees, not more, because otherwise the cart is gonna be super fast and it's gonna jump out of the bumper. This is the motion sensor. Anyone remembers how it functions? We used the motion sensor so far once, right? I need anyone to tell me anything about the motion sensor. How does it function?
That you were very, very glitchy. I did not hear anything.
Oh my God, let me put my video away. Probably you can hear me better. Ooh, video away. All right. Do you think it's better? Can you hear me?
I don't know, maybe. Yes, but I can hear you now very well.
All right. So I need anyone to tell me anything about the functioning of the motion sensor. How does it function? Do you remember anything? You can write it in the chat.
It measures the speed it measures the time it takes for the motion to last.
Okay. Yes. Anything else? Probably Teresa. Teresa, do you remember anything from the functioning of the motion sensor?
Not too much.
Okay. Probably Yorgo can remember the motion sensor.
I can hear the question.
So the motion sensor, how does it function?
It detects if an object is moving and its speed.
Exactly, exactly. But how does it do it? It has an eye, it has an ear, it has what exactly? What does it sense? You can't remember. You can write in the chat, Giorgio.
I think it has an eye.
Actually, it has an ear. Not really an ear, but it sends ultrasounds and it receives ultrasounds. We cannot hear those ultrasounds because they are sounds, yes, but not, you cannot hear them because you're simply human. And knowing the speed of the sound, the motion sensor can calculate the time taken, exactly what your friend was explaining, for the sound to go and come back. In other words, the motion sensor can give you an XT graph, a VT graph, and an AT graph. Okay, fine. All right, so we're gonna put the motion sensor on top of the track, which means the cart is gonna slide down, actually will roll down. What will happen? We're gonna see an increase in the distance between the motion sensor and the cart. And let's see how things would be. This is while it's going down. What happens at the end of the track? Can you guess? Anyone? What happens when the cart reaches the end of the track? Very easy question.
We finally put zero.
Rebounds. Who said rebounds?
Me, Michelle.
All right. And Selena is saying it's gonna stop. To be honest, it's gonna bump into the bumper and it's gonna be a collision. It's gonna be a strong collision. It's gonna be loud, like a boof collision, and it's gonna start moving upward, slowing down, and it's gonna stop before reaching the motion sensor, and again it's gonna go back down. So it's gonna keep on going up and down, boof collision, up and down, until energy is gonna, it's gonna lose energy for after every collision, and eventually it will stop, like Selena predicted. All right, so we're gonna have a collision on the bumper, and if the cart is very fast, probably the whole track is gonna move in, and we don't want this to happen. Because if the track is gonna move, the angle is gonna change, and you want the angle to be a constant. So we need to make sure that the track is very rigid, probably attach it to something rigid like a wall or something, okay? This is what you will get. It's an accelerated motion. And I mean by since you have acceleration, can you remind me what was the acceleration? I think Andrew knows. What is the acceleration for an inclined plane Andrew.
Sorry, miss, what?
What is the acceleration for an inclined plane? The acceleration of an object sliding down on an inclined plane. Anyone else?
G sine theta.
Yes, this is what I was expecting you to say. It's G sine theta. Thank you so much. Now, Teresa, this acceleration, is it constant or zero or a variable?
I guess it's constant.
Yes, because gravity is constant and the angle must be constant. So it is constant acceleration. I'm gonna call it just constant. Now, if you have a constant acceleration, do you have a URM or UARM? And what I mean by URM is uniform rectilinear motion. Let me see if Magali can answer. Magali, do we have a URM or UARM?
URM.
It's a UARM, Teresa saying, because we have acceleration. So URM is uniform, and every time we say uniform, the acceleration is zero. In this case, the acceleration is not zero, it is a constant value. It will be around 0.2 meter per second squared for small angles. It can go up to 2 for bigger angles. So we have acceleration. What we have here is UARM. For UARM motion, we have those to be the kinematics equation. V is linear in time, and X is, you see the quadratic equation, it's not linear in time. That's why the XT graph is gonna look like a curve, and the VT graph is gonna look linear. Okay, you see the constant slope? Now tell me a bit, and I believe this is very important. What is the slope in an XT graph? So the slope in an XT graph. Probably I need to ask Nassim. Nassim, in an XT graph, what's the slope? Slope in an XT graph. Nassim, are you there? Okay, can you write in the chat? You can say, I don't know. It's okay, I'm not quizzing you. The slope in an XT graph. Giorgio, can you tell me what is the slope in an XT graph?
Yes, it's velocity.
Yes, and you see the velocity is changing. The thing is speeding up. Giorgio, stay with me. What is the slope in a VT graph?
The acceleration.
Exactly. All right. This is all I need to know for the moment. We need to know acceleration, and the slope of a VT graph is enough for us. All right. So basically, these are the motion graphs in theory. However, in practice, we're going to get something a bit different. Let me move this to the side. This is a VT graph, okay? Because it's not visible. And this is an XT graph. All right, you see something T squared. This is while the cart is moving down the incline, getting farther from the motion sensor. Let's say the motion sensor is at 0. Yeah, so it's getting farther from the motion sensor. This quick change, sudden change in the slope is when you had a collision. So you have a collision, it gets closer to the motion sensor. The motion sensor is here, it's getting close to it. Then it's gonna stop. This is 0 slope. This is where it stops for a second, and then it's gonna come back down. All right? So this is a bit difficult to understand. So you can see it in here. The position, the XT graph, this is XT graph. It's going up the incline, then down the incline. You can see down the incline because it's speeding up. How do you see it speeding up? The slope is positive and increasing. So velocity is positive and increasing. All right, let me know if I'm glitching. I can turn my video off. For the velocity time graph, this is down the incline. Speed is constant, is increasing. However, the slope is constant. So the speed is increasing, but the acceleration is constant. Okay. The sudden change in the slope is due to the collision. So here you have collision, COL. And suddenly the velocity changes from positive to negative because it was going down. Suddenly it starts moving up. And you see that the velocity is decreasing to 0. This is where you have a 0 velocity. By the way, you can watch the recording again and pause and write down the description if needed. And this is speeding up again. So this is up the incline, down the incline. So if I take this marker, everything above the x-axis here is down the incline because we took down the incline to be our positive direction. And everything below the 0, below this line actually, by the way, this is where the 0 is, and everything below the 0 is negative. So everything below the 0 is up the incline. What you want is the acceleration, and the acceleration is the slope. So if I take the slope here or here, it's gonna be the same. Don't you notice that they are parallel lines? Yes. So what you will do is the following. You're gonna take those. So this is a real picture from the lab, and you're gonna select this part. And Data Studio will give you the slope directly by simply clicking find the slope or click linear, and you need to select the line you want. All these lines will give you the same slope. Just pick a line that you like. Make it like pick a line that is long enough. I don't like this one because it is full with errors. This one as well, you can see some errors. This one is really flat. So if I were you, I would want to pick this one. This one is nice. So you simply select it and click on slope, and it's gonna give you the slope. So this is how you do the acceleration. You're not supposed to do any calculation. This is the XT graph, just for you to observe and understand XT. And this is the acceleration T graph. And you will notice that the acceleration is constant. Then you have collision, constant again, collision, constant again. And you see the acceleration lines are getting smaller and smaller and smaller because the energy is, you're losing energy after every collision. And energy means the cart is going not really up the incline, but a bit less. Okay? All right. Am I still glitching?
No.
All right. So how do we measure the slope experimentally? Magali, to measure the slope experimentally, actually the acceleration experimentally, what do we do?
Have to do rise on run and calculate.
Okay, acceleration. So we're gonna take the VT graph, not any other graph. This is one, and find the slope. Okay, this is what you meant. And find the slope. However, we don't need to do rise over run. If you want, you can do rise over run, but Data Studio will give you the graph with the slope without any calculation. Okay, no need to calculate because Data Studio will do the work for you because it does it a bit better than rise over run. It's gonna take the best fit, and you just need to select to tell Data Studio which point to start, which point to finish. Do you think this makes sense? Next time I see you, I'm gonna leave you to do it on your own, but I'm gonna definitely pass by and do one trial in front of you, okay? You will have to fill in this table. What is the mass of the cart and the uncertainty? I need to ask Yorgo. Yorgo, how do you find the uncertainty of any measured value? Can you brief me quickly? Uncertainty.
You mean the RMS error?
This is a measured value, mass of the cart. RMS is the, all right, so the RMS is the uncertainty for the average, and we're not doing any average. So the RMS is the uncertainty for the average. We're gonna do the average later, but here, the mass of the cart, how do I find the uncertainty of the mass?
It's the smallest division divided by 2.
All right, it could be something similar if we're talking about an analog measuring tool. What if we're talking about a digital measuring tool? So uncertainty, it's gonna be smallest subdivision, that's what you said, right? Subdivision divided by 2 if you're talking about an analog measuring tool. But if it's digital, we simply take the smallest subdivision. Okay, So Miss Jinan, after writing the mass of the card, on the card, she needs to tell us, did she use a digital scale or an analog scale? I would tell you that Miss Jinan will definitely use a digital scale. So whatever you see written on the mass on the card, it's gonna be digital. For instance, 582 grams. What is the smallest subdivision? So let's say, let me pick a pen, and let's say she wrote 582 grams. Can you guess what is the smallest subdivision? What is the smallest value this measuring tool can measure? Just guess any value. What do you think? What is the smallest? It's the 1 unit, right? So it's 1 gram. Okay, so for digital measuring tools, the smallest subdivision is the uncertainty. For analog measuring tools, you need to look at the tool to see what is the smallest subdivision to be able to divide it by 2. Okay, so those values are not real values. You will find the real value when you come to the lab. Also, you need to measure, you need to pick a certain inclination, angle, theta, and degrees. You will use a protractor. Is the protractor analog or digital? The question is for Selena. Is the protractor analog or digital? She said analog. So how do I find the uncertainty on the angle? Is it smallest subdivision divided by 2 or smallest subdivision, Selena? Divided by 2, that's so right. So you just look at the protractor and see. Now you're gonna do trial 1 to like repeat the same experiment 5 times. You will get a graph as such, and you will find the slope in each case, and you will fill in the table, slope, repeat, slope, repeat, slope, repeat, slope, repeat, slope, repeat. It's gonna take you 5 seconds. And then you do the average. Everyone in this room showed me beautiful lab reports. I assume everybody knows how to find the average and how to find the error on it that we call RMS. I suppose. If you don't, please feel free to ask me. I'm willing to do the work for you and to help you with it. The average of the slope is the acceleration, experimental. What is the theoretical acceleration? I think the expert here is Andrew. Andrew, can you please remind me what's the acceleration theoretical? Andrew, are you there?
Well, I don't know.
Well, you just said it a few minutes ago. What's the acceleration on an incline? What is the
G sine theta?
Yes, this is what I was expecting from you. All right, and it's okay to say I don't know. All right, so the acceleration is G sine theta. You're gonna do the experiment and you're gonna do the calculation, and you will compare those two values. Are they similar? And they will be very close. Okay, now they will ask you to find the uncertainty of this one. I will help you next week. Let's not do it today. Okay, then you're gonna pick acceleration 2, angle 2, repeat, angle 3, repeat, and please stay below 10 degrees. I know 10 degrees is small, but your cart is very fast. The experiment is very difficult when the cart is fast. All right, the next part is they want you to add a bar of mass, extra mass to your cart to see the effect of mass. If you keep theta 3 the same and you add an extra mass to your system, do you think the acceleration is gonna change? Let's ask Andrew again. Andrew, what is the acceleration for the incline? Yes, Andrew, how do I find the acceleration for the incline?
Sine theta.
Yes, Selena, you can go. So it is G sine theta. Okay, so look at it, Andrew. My question for you is it mass dependent? Do you see any mass in it? Probably
No mass.
Yeah, no mass. So if I add a mass acceleration should not change. However, in the experiment, you're not dealing with an ideal case. Probably you have friction. Probably if you have friction, mass will affect your motion or not. We don't know. We want you to try. For some benches, it's gonna be changing. For some benches, it's not gonna be changing. And eventually you're gonna answer a list of questions and you will explain if it's mass dependent or not. The final question is devise a procedure where the mass actually changes your acceleration. And here you need to come up with a thought experiment. You need to draw a sketch of the setup, explain, use Newton's second law to explain why the acceleration depends on M. Probably you can take a horizontal desk, a pulley, a cart, a wire, an extra hanging mass, anything, an experiment of your choice. Very briefly in a paragraph, you say, if I do this, I will end up with this, and you explain Newton's second law to say why acceleration depends on mass. This is not difficult. It may be tricky a bit. If you need help, please let me know. We can do it together. Okay? So back to motion on an incline, you need to know the forces. You need to know how to break down mg into mg sin and mg cos. Normal and mg cos cancel out because no motion is happening along the y-axis. The remaining force is mg sin. This is ma. You cross out the m's to get a. If you don't remember what a is, you ask who? You ask Andrew, all right? You use the motion sensor. I'm gonna probably remind you about the functioning of the motion sensor. This is how you need to put your setup. I will ask Ms. Gina not to construct this setup for you, to give you the equipment detached, and you will connect them together because I think this is part of the fun. And then you're gonna start and you're gonna get those graphs. If you don't get any graphs, I will help you with that. You will observe the graphs, you get something similar. And then I think it's easy. I'll show you how to find the slope and you can fill in the table directly. Okay. And probably I'm gonna ask one group at a time to do this experiment and to fill in the table. So next week we have a lot to do. For this week, you need to complete lab 3. Do you think you can complete lab 3? Do you think you can do it in a couple of days? All right, I'm gonna stop recording for the